Hello and welcome to C++ 101 Week 6. I'm going to be here, and my name's Nelson, and Gavin's going to be here.
Hey! Week 6, hurrah!
Yes, Week 6, the dreaded Week 6, when we're going to be talking about pointers. And pointers are typically one of those things that you hear starting off learning C or C++ that sound really scary, and this week is dedicated to making them not scary.
Shift 8, that's it.
Okay, so let's go ahead and fire up Visual Studio and start talking about pointers.
What's the point
Yeah.
of pointers?
Basically, throughout this class, we've sort of been alluding towards the idea of allocating additional memory that we do not know ahead of time, but when our program is created. So what we have is a bunch of problems that need to be solved by allocating additional memory during runtime. A pointer is the means in which we do so. The pointer is a means in which we can reference or point to additional memory that's been allocated outside of our program. So we've already a bit talked about the stack. So now we're going to be talking about the heap a little bit. But first let me go ahead and do a quick little demonstration of one of the fun things we can do with pointers, and then we'll back up and talk about it a little bit more. I'm going to go ahead.
That's good, because I already still don't know what they are. There's certain aspects of the free jazz drum solo to your keyboard. Someone like Cozy Powell or someone like that.
Okay, can anybody guess what the output of this program will be, given that I had typed in a particular string on line 13? Take a look at that code and guess what's going to happen.
Go on, guess. Now, guess. I'm doing excitement, can you tell?
Yeah. Segfeld, I know you know that that's wrong.
And that's not a guess. Oh, that's a guess. That's not a guess, though. I mean, this is a guess isn't a guess.
Okay, so I'm going to go ahead and hit a 5. Okay, did everybody see that? Nothing.
Slim Shady of console apps.
Now, I won't get garbage because strings are actually initialized to an empty string value, so I won't get garbage.
But the key thing is what you won't get is the word product.
Yes.
Is there any way around that? That's what you call timing. Just as you type that, Musaru said, "This is like a horror movie. I know the pointer is there, I just can't see it yet." Literally appeared on my screen at the same time as your asterisk. Hurrah!
Okay, so what did I just do? What I did was I wrote another function called getProductName2, and instead of taking a product, it takes a product pointer. We know it's a pointer because of this star modifier attached to the type. Just like
Asterisk.
Asterisk. Just like
Asterisk.
asterisk. Just how we can modify types and turn them into arrays, we can also modify types and turn them into pointer types. So this product type right here is a pointer type. Now you'll notice, well, it is a dereference operator, but in this context it's not actually dereferencing anything. So you'll notice that on line 19 I used this instead of dot. This arrow is very, very important. Whenever you're using a variable that's typed to a pointer type, you must use the arrow to access the data that this pointer is pointing to. So you'll notice this new symbol has appeared. In addition, we also have another symbol appearing on line 25. You'll notice that if I were to try to build without that symbol, you would get a compilation error. It would say, cannot convert parameter 1 from product to product pointer. That's because a product is not assignable to a product pointer. What is assignable to a product pointer, however, is the address of a product variable. This operator returns the address in memory of any object or any variable. So how's everybody feeling about this so far? Because by doing this, well, actually not really because we're using structures, but we've made it a little bit more similar to what people would expect if they were writing in Java or C#.
I was going to say, in comparison with C#, just to wind up the people who don't like me comparing it to C#, I've decided to do it in every possible occasion. But this is the equivalent of using a C# ref keyword, presumably.
Kind of. It does have similar behavior, it really does. But refs are a little bit different. Refs are more like pointers.
You mean pointers to pointers?
Yeah, refs are more like actually assigning a variable to something instead of actually accessing a common piece of data. This is just like using a standard reference type in C#.
Ah. Okay.
Okay, so what's going on here is very important. What we're doing here is instead of passing in product by value, as we would here, where the members of product get copied into the stack frame that gets allocated when the getProductName1 function is invoked, we are now passing it by a pointer, where we are now reaching in and grabbing data that's actually resident on the stack frame that isn't in this stack frame. So notice we can do some fun stuff with pointers. So for example, if I were to go ahead and get a pointer type, we can do this. So what this is doing is this is creating a pointer type to a reference of P1. So if I were to see out this, we would get something really interesting. Now notice that I'm not printing any member of P2. I'm printing P2 itself. And you'll notice that cout allows us to print pointers. And when we print a pointer, we get a number. And this number represents the address in memory that that data is resident in. Oh, you can declare custom types in C++. Last week we covered enum types and struct types.
Can you see the answer that I previously wrote to him that was a response to? You need to get your columns.
So pointers are references to memory instead of the content of the memory. Yes, they're references to other bits of memory. So what we're doing here is in main, when the main stack frame gets pushed, we get the memory that's required to store a product made available to us. But then what we're doing when we invoke getProductNames2 is we're passing a reference or a pointer to a bit of memory that's allocated on a different stack frame. So even though main stack frame will get deallocated once main is ended, during main's execution, the stack frame is still valid. Therefore, we can reach back up the call stack and grab data that's allocated on a different stack frame by using pointers.
Right. You're going to hate me for saying this. I really think you need to get the whiteboard out as soon as possible.
I don't know if I can.
This is quite a confusing concept.
Somebody did ask, though, about this. This symbol is an operator that reaches in and yanks out the data that this pointer is pointing at. Okay, well, I'll try to whiteboard this out.
The trouble is, it's such a nebulous concept because it's not something you can really, it all happens behind the scenes. And just it's somewhat clearer, I think, to see that, or at least see that there is a difference in C++. It's more obscure in C# because obviously it's
Everything
it helps
in C#.
you. Everything's
A reference
like
to C#.
that.
Okay, so let's go ahead and talk about main. Main has a product P1 on it. Now, this is the stack frame for main. So the data available or made available to us is via our definition or declaration that we have a product variable is represented there with the product P1. Now, when we push on the other stack frame for the get input other function, so other function, we push on into this function a reference to this memory. This gets stored in a product pointer. Wow.
The little bloke. He's the man pointing to the product, like one of those guys with a golf sale sign.
So we're reaching in to main. So when I say P1 pointer, or this notation, to name, this notation is asking the pointer to dereference itself. And by dereferencing the pointer, it goes all the way back and reaches in to where the data actually is in memory. So how's everybody feeling about this?
Can you just go through the equivalent that would happen when it's not a reference you're passing?
All right. So if we have another case where we're not doing a pointer, and by the way, try not to use the word reference because a reference in C++ is actually different. It's a different concept. There's a thing called a reference. Okay, in the case of no pointer, this product P1 gets copied into the stack frame of function. So then when we do P1 dot name, this symbol is meaning reach into the actual memory that was copied into. So doing P1.name is actually going to jump right into the memory that was allocated when the function stack frame was pushed, and that memory happens to contain a copy of main. When this stack frame goes away, when it gets popped back up to main, that data is erased. In the same way here. This data is erased when the stack frame gets popped. But the difference is because the entire time we were editing the memory right here, this memory is still resident.
I was going to say, presumably before either of them were popped, so when the two functions still are in existence, presumably in terms of the amount of memory they take up, the one on the right, the non-pointer version of it takes up more memory.
Yes. This is
Whereas on the left, it's using memory directly from main.
I believe it's 32 bytes for a string. I'm just going to guess. So this is going to have 4 bytes, and this is going to have 32 bytes. And the difference is that a pointer on a 32-bit operating system or a 32-bit build is going to be 4 bytes. Whereas in the case of a copy operation, the entirety of product, the entirety of the data within product gets copied onto that stack frame.
That's probably if you're having trouble getting to grips with, or if you think you're going to have trouble remembering when to do what, that's a key thing to remember, the difference between the two of them. Because the reason that you've only got those 4 bytes of memory used is because it's a pointer. It's pointing back out to main, to the memory there.
So saying ampersand P1 is passing a reference into the function. A bit, yes, you can say that, although avoid using the word reference, because a reference is a different concept in C++. A dereference is when you dereference a pointer. And a dereferencing can be done in 2 ways. Either you can do P1 and then use this symbol to dereference it directly, or you can use the star notation again, P1, wrap this in parentheses, and then do dot name. The difference is both of these do the same thing. They're both dereferencing. The difference is this is dereferencing the pointer, wrapping it in parentheses so that the dereference takes precedence in the order of operations, and then using the simple dot notation that we saw before. This is just a cleaner way of doing that, of accessing a member directly.
And although it's not something we're covering in detail, or in what detail there is in any of these courses, if you're not sure on order of operation, mathematical order of operation, Google it, Wikipedia. There's plenty of very obvious sources for this information. It is something that you will just need to be able to use. Just thought I'd mention that because it's something that we sort of touch on, like there, for instance.
Okay.
But, or indeed, you could buy the math videos from 3dbuzz.com, which are very good.
Since you're using a pointer, you don't need to return the variable which you passed into the function operator. Yes, because I don't need to return anything from this. This function needs not to return anything because he is reaching into the personal space of another stack frame. Whereas with this, the only way to get this to behave properly is you would have to return edited product, which will result in another copy operation.
You see, that's what made me think it was like passing by reference in C#.
Well, yeah, it is. But, or do you mean the ref modifier?
I mean, with the ref modifier, that difference there that you just explained.
Well, the ref modifier is a tad bit different because it actually assigns something to a variable. It doesn't assign something to the same memory that a variable is pointing to.
Right, okay.
So there's a small distinction, and my tablet is wigging out, so hold on.
You've been doing very well today.
Okay.
Flash, if you get it, just run with it and assume that you're getting it. It is actually, it's one of those, it's a bit Wizard of Oz. It is a very straightforward concept. But
The application.
if you can't see it immediately, you can stare at it for ages. A bit like a stereogram. You can stare at it for ages and just not see it. And yeah, like Nelson was going to say there, the application of it is
entirely different.
Yeah.
So P1 is the actual object on the pointer and not the copy. Yeah, P1 in this case, this is the memory that's being used. And hold on, I think my VM stole my tablet.
Well, run after it and get it back.
Give me my tablet back. There you go. So this memory that's allocated on the main stack frame is the only product memory that is actually being allocated in this example. So would you say if you point to a variable you never lose scope, or does the address ever get lost or such? It depends if you're dynamically or statically allocating memory. In the case of this stack frame, we are statically allocating the memory that's going to be used for product in the main stack frame, meaning once the main stack frame is popped, that memory becomes invalid. So for example, if I were to write a really stupid program that had a function stack frame that allocated a product and then returned a pointer to the caller. So let's say main has product pointer equals function. So that's main. Now let's say the function returns a pointer to the product that it allocated into main, into this pointer. When this stack frame gets popped and is no longer there, that product pointer is no longer pointing to proper memory. So if we returned a pointer, that was pointing to memory that was allocated on the stack frame, and that stack frame was popped, that memory is no longer considered to be valid. And this is a problematic piece of code. There are a lot of symbols that make it more complicated to follow. Yes, there are a lot of symbols in C and C++ that all do things that are related to each other but change drastically depending on context. Wouldn't it crash your computer then when it pops off? Not necessarily. Just because a pointer is pointing to a memory address that is, for all intents and purposes, considered to be invalid, that doesn't mean that that memory space that you're pointing to can't be repurposed for another reason. But in that case, that means you're just reaching into garbage memory. Returning a pointer is a valid thing to do if you are dynamically allocating memory. So far, we haven't done any dynamic memory allocation. But if you dynamically allocate memory, then it's okay to return a pointer. Why would we have to pass reference P1 into the arguments? Why not only P1? Because cout can print the address with P1 and not with reference P1. It's the symbol. Again, everything has different connotations depending on context. So for example, P1 is a product. Whatever. Ampersand, which I'm going to fail at, so...
P1's a prod cut. That's fantastic.
I don't know if that's an I can't draw an ampersand.
Draw a treble clef instead.
Is that what a treble clef looks like?
A treble clef looks like an ampersand standing to attention.
Isn't it like something like that? Or something?
Let's stipulate. Draw a backwards 3 with a line through it, a vertical line through it. No, backwards 3.
That is, oh, my backwards got backward.
Backwards. That's near enough.
Okay, so ampersand P1 is an address. Oh, God.
Well, you see, an ampersand is an E crossed with a T, because it comes from the French et, meaning and. God, I'm fascinating.
That's an address to a product. So yes, it does get confusing, but these are symbols you're going to have to realize. And C++ could, in theory, not require you to use the ampersand when passing a object or any other variable into a function that expects a pointer of that type. The compiler has enough information to know to do that conversion for you behind the scenes. However, that's just not how C++ is. C++ is very explicit. That being said, things do change slightly when we're talking about C++ references, which are similar to pointers. So, yeah. Okay. Blah, blah, blah.
Are there situations where you would want to copy the variable?
Yes.
That's all that was asked. So that's as good an answer as any. Next.
Well, yeah, copying by value is important, but it's not. Generally, you work. Typically, you work a lot with pointers in C++. A lot with pointers, and you'll notice that there are some great attributes of pointers, especially when you talk about performance. Because in the case of pushing that function on the left onto the stack, what happens is all we have to do is copy 4 bytes on a 32-bit operating system. We have to copy in 4 bytes. That references memory. So that's going to be significantly faster than the one on the right, which copies that data. That being said...
I was just going to say, and imagine if product wasn't just a product. Imagine it was a database of Amazon's products. You know,
Right.
That's a hell of a lot to shift. Whereas here you can do a lot of the work with just the pointer.
Then again, pointers do introduce interesting problems, make multi-threading difficult because you're sharing memory. There are a lot of situations where pointers aren't desirable, and you decide that taking a performance hit is a greater benefit than some of the potential errors that you might run your program into. In fact, who's that guy? Camrak. He recently did a article about functional style programming. And functional style programming in C++ more or less means using fewer pointers. When you copy around immutable data rather than pointing to it. Even in that case, though, if you copy around, let's say, a immutable class by reference or by pointer in C++, if that class locks down its data, then you have fewer risks. So it really depends on the situation. Why did the pointer get off there? Why is it not pointing to the right memory? I don't know if...
I think that came in when you were doing the lower left diagram about returning.
Well, right. What happens is this memory, when the function gets invoked, this memory gets allocated. When the function returns, this memory gets deallocated. Because this memory gets allocated and it asks for a product, that product's reference is being returned. That means when this memory gets deallocated, it's no longer pointing to what you should consider valid data, even if it technically may be or may not be. So use ampersand to get addresses, work with pointer arithmetic. If not, what would be some of their usages. I do want to point out that the ampersand symbol in C++ will confuse you because the ampersand symbol is used for C++ references, as well as, in some contexts, C++ pointers. Horrible choice of symbol.
Is it also
usage.
used as a bitwise AND operator?
Yes. And it's also used for the short circuit logic AND operator. Well, two of them anyway. So you use it to get the address. I don't use that operator very often in cases other than passing a object that I allocated on the stack into a function that accepts a pointer. In that case, the ampersand symbol is very useful, but other than that, I typically don't have very many other use cases that I can think of.
I think you should set up a basic couple of objects and get them to write something that passes them around.
Yeah. First, though, I do want to code out this example because I think this example is more clear in code than it is in diagrams.
Okay.
So let's say you had a function that returned a product pointer.
Yes, just to emphasize, this is an example of bad.
Yes. Again, returning a pointer isn't necessarily a bad thing because it's very useful when you're working with dynamically allocated memory. However, returning a pointer to memory allocated on the stack frame will cause you lots of misery. So you'll notice here what I'm doing is I'm allocating a product object on the stack. So when this function gets invoked, the memory required to hold my product variable is allocated for me. And then you'll notice I immediately turn around and return a reference to that. So now if I go ahead and do product P11 equals, why would you ever do this? And product P12, why would you ever do this? Now if I cout them, you'll notice something interesting. I'm not sure if this what is going to happen is entirely dependent on the implementation, but I'm thinking it'll do what I want it to. Yes.
Really?
It did.
What it does is dependent on how it's designed to do it.
Well, no. What it does is not a defined behavior. It's a behavior that's entirely up to the implementation itself and not the specification. But you'll notice here. Okay, does everybody see what's going on? I'm invoking the why would you ever do this function twice and aliasing them out into two pointer variables, P11 and P12. Now notice on line 33, I print out P11 and P12 to get their memory addresses. Look at this. The memory addresses are the same. Meaning I just entered a situation where two pointers that should be different bits of unique allocated memory, they're now going to be the same. And that's not necessarily true. For example, if I had invoked this, like for example, if I did this, actually that's going to be the same, but if I invoked this from another function, so I said void ble, and did this, you'll notice that there'll be different memory addresses. So you'll note they'll be the same, the two will be the same, but they'll be different from main, because the stat frame has been modified by pushing ble onto the stack, and then from within ble invoking why would you ever do this.
And have you just essentially lost track of a chunk of memory?
I haven't lost track of it. It's not a memory leak.
Right. I was going to say, can you get back to it?
Yeah, it's not a memory leak, but it's just us pointing to unallocated memory. It's us pointing. It's not a memory leak in the sense that we created additional memory, never gave it back, but it is something that's called a dangling pointer, where we are pointing to unallocated memory. And that memory could do anything. And Musuru thinks that was just really funny, apparently.
I just love the fact that in Chris's question about it, he spelt leaks like you'd expect him to, being Welsh. But anyway,
so why do they point to the same memory? They point to the same memory because of the way the stack frame gets allocated. So if we jump back into this, you'll notice that when we invoke this function, that gets pushed onto the stack. And then the product memory gets allocated. And when the product memory gets allocated, we return a pointer to that product, to that data, right there. And then when it gets pushed again, it just so happens that that stack is going to be pushed on relatively the same memory that it was before. Because basically what we're doing is we're calling a function, pushing this onto the stack, popping it off the stack, and then pushing it onto the stack again. Because the location of main never changes and the stack frames are allocated relative to each other, you'll notice that what's going to happen is we're going to be pushing this function onto the same place both times we invoke it. What if you alternate it? Like call ble once, do the cout in main like you have now, and then ble again. Is it going to have 3 different pairs of addresses, or one pair going to be called twice? It's not going to matter. Because again, when we push relative to, when we push the stack frame relative to main, it doesn't matter from wherever in main that other stack frame is allocated, it's going to go on the same place. But because we invoked ble, and ble invokes why would you ever do this, ble's position relative to main is further down the stack. So that means then when ble invokes why would you ever do this, this function gets pushed even further down the stack from when it was invoked from main. Are you saying that function is pushed onto the stack? Yes, functions are pushed onto the stack. All the memory required to contain the variables that we declared within a function, all that memory is allocated when the stack frame gets pushed on. And the stack frame gets pushed on, and as a result, that memory then becomes allocated. When the function returns, that memory becomes deallocated and repurposed. So does doing ampersand p print the address of the actual pointer where the pointer points? This is going to print well, actually, hold on, because now we can get into some really weird stuff. If this isn't already really weird. Okay, so cout p2 and cout ampersand p1. These will print out the same thing. Printing out a pointer is the same thing as printing out the address of a non-pointer. However, there's nothing stopping us from doing this right here. Can anybody guess what's going to happen when I run this? Can anybody guess what address is going to be printed out? Not exactly, but explain your reasoning. Yep. This is called a pointer pointer. This will print out the address of the actual pointer variable itself.
which is just before the pointer.
Yes. Well, yeah, that's how it works, because you'll notice the address of this actual pointer is declared immediately after the product, which means that they're going to be very close together in memory.
So the third line is the pointer to the pointer.
Yep, it's an address to the variable P2. Because remember, pointers aren't magical things. They still are variables. And again, on a 32-bit operating system, they'll be 4 bytes wide.
I just kind of, I'm just getting my head around why it's a lower memory address.
Depends on which direction the stack is allocated, and the implementation of the C++ compiler itself.
Oh, right. Well, I find that interesting.
Yeah, pointers
Okay.
are 4 bytes of memory on a 32-bit operating system. Which means that line 39, no matter how big the product structure gets, now in line 38, if the product structure gets bigger by us adding more fields to it, that'll increase the amount of memory that's allocated for P1. However big the product structure is irrelevant, because all we need is a reference or a pointer to a product object.
And the pointer is on line 43. It's the ampersand P2, because it's a pointer to a pointer.
Yes.
Ampersand P2 points to P2. But if you look on line 39, we're setting P2 to be a pointer to P1,
Yep.
which makes the pointer to P2 a pointer to a pointer, thus a pointer-pointer. They're sisters.
And of course, you can have a pointer to a pointer, to a pointer, to a pointer, to a reference, to a pointer, to an array. I mean,
It's all right, Segfield's not here at the moment. He's missed the one bit that he's been banging on about. I'm not actually old, Liam. Look, set them something to do. Give them some work. They're getting lippy.
well, here, let me
Make them do something.
Let me finish some questions, and then we can go on, because then it's about time for break after I do that. So to see out ampersand P point, okay, I answered that, hopefully. So the variable on the memory that is returned is empty. Would it cause an error if we tried to use it? Maybe.
That's not helpful.
But it's true. Maybe.
I know.
Think about it this way. You can, let's just say, okay, so a float is 4 bytes, an integer is 4 bytes. Meaning, we could technically address the memory of a float, but cause the compiler to think it's an integer by using a pointer. What we're doing here is what we're getting back is memory that we're telling the compiler to treat as if it were a product. But that memory is conceptually unallocated. It's unallocated, undefined space that could be repurposed for any other purpose, or could be reused for any other purpose. Meaning that although we're convincing the compiler to treat the P11 variable as if it were a product, the data that P11 is pointing to isn't necessarily going to be a product and could be changed by any other means. What is the pointer pointer? The pointer pointer is this, because it's a pointer to a pointer. Well, specifically, it's an address to a pointer. We're not going to be talking about auto pointers in this class. Auto pointers are going to be something that will be very interesting. I think they're kind of neat, but they don't. To explain them, we would have to go over classes and templates, and yeah. Why would I want a pointer to a pointer? Nah. I'll be honest. I haven't used a pointer to a pointer in very many production bits. But for example, DirectX uses a pointer of a pointer. So what it's doing is it's saying, DirectX, when you initialize a DirectX or a Direct3D device, what you do is you tell DirectX, I have a pointer variable right here. Fill my pointer variable with the memory address of something you have allocated for me. And now I'll continue to use my pointer variable that has now been modified because I gave you the address to my pointer. I'm assuming to a pointer to a character variable would just be silly instead of just passing a value. Since a character is 1 byte, it depends if you need to reach back in and modify the character, like what you see us doing here with our get product name to method or function. If you need this behavior, the only way to do it is either via pointer or a reference. However, you are right in saying that a pointer to a character is actually going to always be larger, on modern CPUs anyway, than the character itself.
Two more questions.
Okay, so instead of returning a pointer, you would modify what was stored in the directory the pointer was pointing to inside the method. So instead of returning a pointer, you modify what was stored. Oh yeah, yeah, you could do that. That's like I said, that's what a pointer is for. A pointer is for modifying another person's pointer, for reaching in, transcending the stack frames, grabbing somebody's pointer, and saying, you now point to this other thing.
And here's a great question. How can we know that address location a pointer points to actually holds the value or object we expect, since there seems to be a lot of things able to access that particular piece of memory if it's still there?
You don't. You just don't. You don't.
You just use private as in as many places as possible and lock people out of your code so that they can't break it.
Oh, that doesn't mean someone can't use pointer arithmetic to reach in and grab your private fields.
Painful. You're just going to show me a magic trick now, are you? Dead beef. Could you not have gathered that from the spelling of it, by the way? I can't believe you counted the letters. Sorry.
Anyway, what I've just done here is I've said, hey, C++ compiler, give me a pointer to somewhere in memory referenced by this address. I have no idea what this address points to in my current environment, but go ahead and give me an address or give me a pointer to something pointing to that hard-coded address and treat it as if it were a valid product. This is completely valid C++ code. The semantics of how a compiler treats a bit of memory is determined by the type system. What memory is actually being worked on is determined by, well, you not failing.
And by the way, dead code, it doesn't. It's a number. It's a hexadecimal number.
Yeah, this could have just.
That's 0x at the start means what follows is a number in hexadecimal. And hex, because it needs to go up to 16, runs all the way up past 8, 9, A, B, C, D, E, F, G.
It goes to F.
Well, it should go to G.
It doesn't go to G.
So that the octave starts over. Anyway, yeah, I got confused. We could do it in base 17. That'd be fun.
Nah. How can we know that the address of a location pointer actually holds a value? Oh, I already answered that. You don't, ever. And many of your bugs, many of your runtime crashes, many of your corrupting of memory will occur because of you using a pointer that points to memory that is either unallocated or inaccessible. As, for example, this program will work up until I do this. This will cause a runtime exception, hopefully. Thank God it does. We get an access violation. We get an access violation because presumably I reached into memory that's not accessible by my current executable. So that's why we get an access exception. This is memory that I can't access. But anyway, you'll notice that I didn't get a runtime error when I did this. C++ was just like, derp, I'm going to put this memory this memory address and stuff it into this pointer. But we do get an access violation exception when we actually try to act on that data. because now we're reaching into bits of my computer that are not meant to be reached into.
It's probably ponies. Right, stop. Right, you see, this is what I knew would happen. More questions come in while you're answering the questions.
So is it Windows that is refusing you access? Yes. Windows is saying either that memory address physically doesn't exist, as in I reached too far into my memory, or that memory address location is reserved for my use, or that memory allocation is not, you don't have permission to access it because you're coming from process X. Then I will say no.
Right, set them something to do, and then we'll do that and have a break.
Yeah. I don't know. Any ideas?
Set them up something.
Well, I have an idea. I have an idea.
Of some sort.
I have an
Go
idea.
on,
I have an idea.
do it.
It does require a tad bit of explanation.
You've got
But
there, start
no,
afresh.
just
so
give me
clear.
Give me one bit.
1 bit. That's a tiny program.
An array is implicitly convertible. Or sorry. To a pointer. An array is a pointer. An array is a pointer that points to the first location of memory allocated for the array. The operator, the index operator, simply specifies an offset, and the index operator may also be used on pointers. So I want people to write a function that takes in a product pointer and a size, loops over all products and sets their name to something, and returns nothing, and then invoke that function with an array. And here's the definition of, I'll jump up here, here's the definition of product, for people curious. Okay, I'm going to go ahead and pause the video and see what people come up with. Resume. And we're back. So it looks like a lot of people got this right. So let me go ahead and just post it. Post the solution, potential solution, or probably in the case of the simplicity of this, my code will probably end up looking exactly like yours. So I'm going to say something like void set product names, product, products, and array size. For int I equals 0, I smaller than array size, I plus plus, products at I dot name equals hey there. Okay, so I'm going to bring this down here. And in fact, I'm just going to go ahead and delete this code as well. We don't need this code anymore. Okay, so then I'm going to go ahead and say set product names products 5 for int I equals 0, I smaller than 5, I plus plus, C out, product I, products I. Oh, right. Okay. How's everybody feeling about this code? Does everybody feel great about this code?
Well, if you were to step through in the debug, would it show you anything interesting about the allocation? I was waiting for a sort of fairly straightforward example to ask about that.
I mean, what do you mean by
Oh,
memory?
well, just will it show you anything interesting in any of your debug windows, like what's getting put where, or indeed the debug order,
Okay.
the order of what happens when itself. I just wondered if there's anything.
Yeah, there's not a whole lot of interesting things going on.
If not, move on. I wasn't sure.
Well, when the stack frame for main is initialized, we get a 4 or a 5 element array, and we pass it in as a pointer, and then we continuously loop through. Now, some people are
Now,
asking.
see, already there it said bad pointer in that array. When you hovered over it had lots of bad pointers in everything.
Yeah,
As opposed to just nothing or just garbage.
That's the string. The internal pointer of the string would say bad.
But what I mean, yeah. So that's what I mean is that's a specific behavior. Is it that? Yeah.
And you notice when I initialize it, then it gets switched back to a proper pointer. Okay, so there are some great questions. Where are the ampersands, and where is the dereferencing operator? Well, what's going on here is we are using the index operator, and I really want to point out that or hold on, let's just go ahead and do that. Come on, it's not going to let me, is it?
What have you done? I glanced away and now I'm confused.
Oh, come on. It's not going to let me do this. C would, but C++ is not. I want to point out that the indexing operation is just you bringing the pointer forward by 1, or you bringing the pointer forward by the size of products.
When you say forward, you mean moving it forward?
So you're no longer pointing at the beginning of the array, you're pointing at an I offset from the array.
It would be the equivalent of doing I times I equals I times
basically it's
in the for.
Products plus I times size of product.
Yeah.
That's going to move the pointer. That's what's going on when you use the indexing. And the indexing does an automatic dereference, so you don't need the dereferencer operator. Okay. Somebody asked, if you didn't have array size, what would it return? I'm not sure I follow. If you don't have an array size, see, the thing is this is why passing arrays to functions is very difficult. Because you can't pass arrays to functions, you can pass pointers to functions. So what's going on here is because a pointer itself does not carry any additional information other than the pointer itself. That's the only information this contains. You have to supplement the pointer with a size of how many elements are within that pointer, or within that array. Why don't we do this? I'll tell you why you don't do this. This is a pointer to a pointer. All an array is a pointer. It's a pointer with some special syntax, with some special type safety checks. But at the end of the day, an array is a pointer. Meaning that we do not... You what?
I was going to say, if you think of an array like a row of boxes, in this case 5 boxes in a row that you can put things in with numbers 0 to 4 written on the front of them, all that the actual array is, in the way Nelson's saying, in the way Nelson means the sentence, is that it's a pointer to the first of those boxes. In fact, it's a pointer to the bottom left-hand corner of the first of those boxes. Each box is so many bytes in width, And in order to find out how far along the shelf you've got to move to be at the next box, you've got to add the width of one box.
Yep. So product star products, so product pointer products, is a pointer to the first item in products, yes. But so is this. Meaning we do not need to use this operator, because this operator in this context retrieves the address of something. We don't need to do this because all an array is an address to something. It already is a pointer. Maybe just to drive it home, I can say this: products2 equals products. And this would work as well. So you'll see what I'm doing here is I'm assigning, implicitly converting an array immediately into a pointer. So it should become apparent why it's not necessary to prefix this argument with an ampersand. In the previous example, blah, 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 you pass a pointer by using an ampersand. You don't use it here. Is that because products is already a pointer? Yes. So all array memory is contiguous? Yes. All array memory is contiguous.
There was a question I just accidentally deleted saying somebody got strange input, a strange output along the lines of product, roduct, oduct, duct, duct.
No idea.
But I just nuked it off my screen. It's about 10 from the end of the list in the questions panel.
Yeah, that's a great question.
So I just thought I'd point out that question so that you could laugh really cruelly in his face.
I'm not laughing at him because he failed. I'm laughing because that's actually a perfect question that segues into a really important discussion.
It is, well, I can guess roughly what's happened, but
what is going on here is he had code like this. Could anybody explain to me why this is the output? And we've talked enough between today and previous classes for you to answer this question. But can anybody explain why the names of these products are being assigned to like this? This is very odd looking.
who's going to be first?
Of course segfault is, but...
Yeah, but he's just very non-specific, and shut up, segfault, anyway.
Okay.
Because that is cool, actually. I quite like that.
Yeah.
I just like that because it's pretty.
Because people are saying because a string is an array. Yes, well, yes, it is. It's a character pointer. A string is a character pointer, which also, because a character pointer is the same thing as a character array, you can say that a string is a character array. And when I say the word string here, I'm referring to string literals, not the string object. The string object is an object that wraps string literals for us and gives us some nice functionality. But this expression is saying, okay, C++, give me an address, give me a pointer to a bit of memory, and because it's a literal, string literal, this memory is allocated statically at the beginning of our program. All strings that appear in your program are made available when your program starts, and then the C++ compiler replaces every reference to a string literal with a pointer to wherever it decided to put that string in memory. And what we're doing is we're doing pointer arithmetic on a constant character pointer. So the constant character pointer is pointing to a place in memory that contains this product string, and then we're appending I to it. This isn't actually appending I to it. This is adding an additional item, or adding an additional value. We're incrementing this pointer.
We're moving along, yeah. We're moving up. And because I increments each time, the first time we move along an extra zero.
Yep.
So we get the right answer. But the second time through, I is now 1. So we find the memory address of that P. Oh dear, I've been speaking to you for too long. We find the memory address of that P, and then we move along I, which is 1, giving us product, and so on and so forth.
And then auto,
What would actually,
and then
I was going to say, what would actually happen if you had an array that was 10 items?
Oh, yeah, this is going to be fun. Oh, we got lucky.
That wasn't what I expected either. Ooh, you daredevil, you. Yeah, what on earth? Is that purely a fluke?
Well, basically, yeah. What we're doing is, let's go ahead and go to 100.
That's a shame, because that was really cool.
And let's see what memory we're looking at here. We're basically...
It should so draw an ASCII pony. What is that it says there? That's on C, program files.
x86, Microsoft. That's probably the a string pointing to something.
Windows.
But anyway, what we're looking at right here is the string table. We're looking at the string table, and just because it so happens that this string is immediately next to other strings, by incrementing that string forward, we're getting references to other bits in the string table.
Yes, we're getting, because that from on line 16 is actually line 32 of your main. I mean, product number 16 is line 32 of main. That's what was confusing me.
Yeah, so product 16, this string happened to be added to the string table immediately after this string was added to the string table, which makes sense. And as a result, as we are walking through that memory, we run into that other bit. So this is actually a very important concept for people to understand. That's so freaky.
It is very cool.
I mean, let me go ahead and just whiteboard this out, because again, this is a very, very important concept.
Well, and ironically, given that we were chatting earlier about, you know, breaking into code and rewiring it, this points up one big thing, one big security hole in right here. As Nelson said earlier, any string literals you've got are statically allocated at the beginning of your program, and then you get a pointer to them, which means that you will find, this is why when you open up quite a lot of file types, if you force them to open in a text editor, you'll find bits and pieces of plain English telling you things like the title of things or the bits of instructions to user and so forth.
Okay, so here's our code. And here's our program's memory. Our program memory gets a string table where all of these strings get placed inside of memory. So the first string we'll get is a product. Next thing we'll get is a stuff. That relates to this string that showed up and this string that showed up. During execution, these two string literals are simply a character pointer to the first character of anything in the string table. More specifically, it's a const character pointer. But we're not going to be talking about const pointers, so I'm going to erase that. Const pointers get very interesting.
We've almost made a string.
You what?
I just like the idea that by the end of this in 8 weeks, learn how to make a string.
So what this character pointer is, it's pointing to the first element. So when cout prints, it gets a memory address. And then it's going to continuously increment on that memory address until it finds a null terminator. However, because these are contiguous blocks of memory, that's how we can access them. So it's actually laid out in memory like this. PROD DUCT
T.
null terminator STUFF null terminator. Each one of these things is a byte of memory.
Just like the at the end of that example, where you had the all
Yeah.
listed line by line.
So when we point to this P by doing product, this gets turned into a pointer to this P. When we increment it by, let's say, 10, the pointer gets incremented by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that means product plus 10 points to this U, which means when we try to print product plus 10, we get the string UFF null terminator. Because this bit of memory gets incremented on until the null terminator is found. So how's everybody feeling about the string table?
Now draw out a four-dimensional array. in two dimensions.
Okay, so that explains this output. So again, I wasn't laughing at the person because he made a mistake. I was laughing because this is a really cool concept, where we're reaching into bits of memory that happen to be relatively valid because this string is placed relatively close in memory to the other valid strings. However, if we continuously incremented that pointer, we would find ourselves into bits of memory that would probably cause a null access file or a access violation exception to happen. Yeah, which will result in a seg fault, at least if you're working on Unix operating systems. Okay. So all array memory is contiguous. Yes, all array memory is contiguous. If array is a pointer, then isn't product star products make that a pointer pointer? No. An array is a pointer, which means this and this are both, these and these are both pointers that point to the exact same thing. A pointer pointer would be a pointer to the actual products variable. Is it really not going to let me do that? It should let me do this, but it doesn't. Actually, that's because I statically allocated this array. If I hadn't, then it would have been different. But you can think about it conceptually like this, if this did indeed compile.
I think it's probably over familiarity is what makes this seem more complicated than it really is. We're so used to looking at a collection or a row of letters as a word or as part of a sentence and so forth, whereas we almost forget that they're separate individual chars, and that's the way that C++ looks at them, as an array of characters. I'm sure there was a good point in there somewhere, but I haven't got the brain power left to work it through.
Okay.
Thank you, Flash. Brilliant.
So I'm playing with pointers and working with the very real possibility of slipping up and getting into memory I'm not supposed to. Will Windows stop me from doing anything too lethal? Windows will stop you from doing anything that will destroy your computer. So don't worry about that. Windows, however, will not stop you from doing anything that might destroy your program. And I've told the story before. where I spent, was it 2 days, working on a buffer overrun where I was sometimes, under some circumstances, accessing and assigning memory outside of the bounds of an allocated array. And under certain circumstances, a virtual function pointer table for an object I had would happen to be in that memory that I was overflowing into, which would make my object, a few methods on my object, not always the same methods, but a few methods on my object, throw an exception if I ever tried to invoke them because they were virtual methods. And as a result, it was incredibly difficult to track that bug down. Ridiculously difficult. This was like a 2,000 line project that I was just kind of playing with. And I was reaching past memory into the virtual function pointer table and on certain occasions, and that would make a completely different, unrelated bit of code fail under very rare circumstances because I was overflowing into other bits of memory. Windows is not going to stop you from accessing other bits of memory in your program. As long as your program owns it, you are free to do whatever you want to it. And those kind of bugs are hard to debug, yes. Very, very difficult to debug. If an array is a pointer, then a pointer to an array should be a pointer pointer. Yes, it will be a pointer pointer. So is this why string builder is needed? Yes. The string stream. It's not string builder. String builder is a C# type, or a .NET type, sorry. A string stream is what you want to do when doing appending and formatting. Sorry, I'm a bit slow today, but product name in the pointer function is like p2.name in the main cout. Well, in the function, I'm still using the member access operator, the dot operator, or member resolution operator, sorry, instead of the dereference resolution operator. And the reason I'm doing that is because I'm implicitly dereferencing my pointer by specifying the indexer operator. So the indexer operator turns the result of this expression into not a pointer to a product, but a product itself, meaning I can use the traditional member access operator to access name. Why the extra skipped line at products 36? I'm assuming that's because this is a new line. That the product name that was actually printed out for line 36 is a new line. I can verify that for you really quickly. Oh, come on. There we go. So what was it? 36 is 10. Yes, I believe 10 is a new line. The ASCII code 10 is a new line, if I'm not mistaken. Hey, Segfault, stop giving out spoilers. Okay, so... No, it's fine. But I was just... We will be talking about dynamic memory allocation, because that's the biggest thing that we're going to be discussing today. Why don't we see null qualifiers on that list? I'm assuming you're referring to the null terminators. Null terminators aren't printed. This null terminator isn't printed. This null terminator is simply an indicator to whomever is printing the string to stop printing the string. That's all it is. It's a null terminated string. So as a result, that null terminator is not going to be displayed on the console under any circumstance. In fact, it has no corresponding ASCII code.
If you remember back to, was it the second or third lesson where we were doing this all longhand with the arrays, and we had to allocate the one extra space for the oh dear. Wow. What's it called?
Null terminated string.
That's it, null terminator. Oh my.
And remember, like C# does not use null terminated strings. C# uses length prefix strings. So I thought that was kind of funny, how you can put null terminators in C# code, but it is a very big consideration when dealing with interop. So not every platform uses null terminated strings, but they're a very common thing within programming. So is address of P2 saying to store or pass the address of instead of the value of? Yes. The address of P2 is specifying, so obviously that example is no longer in existence, but if I were to quickly write a function that took in an array or a pointer to products or to product, and I were to specify a product to be allocated on the stack and then invoke this function, I would have to pass in the address of P2. Because remember, a product is not convertible to a product pointer because they're two completely different things. A product is a structure with a string in it. A product pointer is 4 bytes of memory, at least on my current operating system and build environment, is 4 bytes of memory that points to something that does contain is a struct with a string in it. So we cannot implicitly convert a product into a pointer to product. So instead what we do is we use the address of operator to grab the address of where this product object is. And in the case of our example, the product is on the stack when main is invoked. We're grabbing the address of it and passing it in to a pointer parameter. So product pointer products 2 equals products and main does not become a pointer or does not become a pointer when it's passed into set product names as the parameter product pointer products product pointer products pointer products array products pointer. This is getting really confusing. Is that right? Do you need to have an address symbol to have a pointer? Typically, yes. You're going to have to grab the address of a pointer to make a pointer. All primitive types are... Wait a sec.
That relates to the... Oh, thanks, I got it, just previous to it, I think.
No, it's a different person.
Oh, is it? Okay.
All primitive types are values. Yeah, all primitive types are values. Ooh, but are you asking... Are you
as
trying
opposed to C#?
Yeah, are you trying to compare this to C#? Because if you are, my answer isn't appropriate for that. I'll give you...
Actually, did you see... it's his code question as well that's left.
No, it's a different person too.
It's the same different person, isn't it?
No.
Oh,
They
wow.
look really, really, really similar though.
Oh, okay.
But all primitive types are value. Are you talking about... if you're talking about comparing this to C#, then it's a little bit more complex of an answer. Int val equals 0. Why did they make... I'm just gonna grab this code and dump it.
Yeah, it's been
IDE.
cut and pasted from...
presumably his IDE.
Yeah. If you're going to send us a chunk of code, could I make it and put it in the webinar panel? If you could either paste bin or GitHub it and post the link in there instead, it would be really helpful. It doesn't like formatted code. It really spatters it across the thing. I can't work out why it leaves so much white space. That's all right. It only occurred to me just then to say it, Florin. It bugs me.
Okay, so why did they make dereferencing I, which usually is value of, be assignable from address? Ooh, that's a good question. Because don't format your code like this, format your code like this. You are not using the dereferencing operator here. This is not the dereferencing operator. Although it is sometimes. It just isn't in this context. This symbol being immediately preceded by a type is a modifier to that type and turns this into a pointer type, meaning that this has no correlation to the dereferencing operator. Now, the dereferencing operator is a way to dereference a pointer and grab the memory at that location. It happens to be the same symbol as a pointer symbol.
So this is going to really confuse people. Which one is what?
Okay. Here, I'll just do a really quick example.
Do it and zoom in as well.
Int
Which one is which?
So int number equals 10. Int number pointer equals at number cout star number pointer. This code will print 10, and here's why. First thing we do is we declare an integer variable in main, and we initialize it to 10, the value 10. Then we create a pointer. Now this is important. This is the type. The type is a pointer, an integer pointer. And this is the type of a variable. The variable is called a number pointer, and we assign it to the address of number. So
just like if you were making an integer array, you had to have int and then the open and closed square brackets. Here you're making an integer pointer, i.e. a pointer to an int, so it's int asterisk as
However,
one unit.
Things get a little confusing here on line 26. We're now not using this symbol to denote the existence of a pointer type. Instead, we're using this symbol to dereference the pointer. Meaning we're saying, to read this sentence out in English, we're saying print whatever value is stored at this pointer, or whatever value is stored at what this pointer is pointing to.
I'm going to have to ask Segfault. Did you mean you use the at symbol with arrays, or did you mean at me with arrays? He says, yeah. Which one? Oh, okay. It's just that I funnily enough, the scripting language I first ever used before learning proper programming used to dereference with the at symbol.
Oh, that looks ugly. Hold on.
Yeah, you see, I am determined to go into into ReSharper at some point. I know we're not using C#, and find the settings for columnation and set it up so that it does things like that tabbed. If there's a way to do it, I'm going to find it.
Okay. So let's run down each one of these lines of output. The first thing we have is the address of number. So that is the memory address in which the memory allocated to contain the data that's provided to us when the main stack frame is pushed, because we declared it on line 24. Basically, the data that the memory that number represents is the first thing we print out, the address of number. The second thing we print out is the address number pointer is pointing to. And you'll notice they look very similar. In fact, they are the same address, because we're assigning the address of number to an integer pointer and naming it number pointer. When we print out number pointer without being annotated by different symbols, we get this. And I could even do one more. I can say value of number.
And actually, when this comes back on the screen again, and Nelson's put it to one side, this would be a very good point at which to do a print screen as a reference to which is what and what means what and what you'll get from each.
Okay. So the first thing we print out is the value of number, which is 10. Everybody is good with this. We created the variable, assigned it to 10, printed it out, we get 10 back. Sweet. Next thing, we get the address of where that memory is stored. So then we get this address. The next thing we do is get that address again because we're printing out an unannotated pointer. And because we haven't annotated it with any symbols, what's going to be displayed is actually going to be the address that that pointer exists or is pointing to. Finally, the last thing we print is a dereferenced number pointer by using the dereferencing operator. Again, this is the operator. This isn't an annotation to a type like you see on line 25. 25 is an annotation to a type. It's saying we want an integer type, but we want a pointer type of an integer type. So we want a pointer of int, is what we're saying on line 25. What we're saying on line 30 is different. We're saying we want to grab whatever data that pointer is pointing to, and we want to yank it out. And we do that. We dereference it and get back 10. So a star after a type is a pointer type, and a star before a variable is dereferencing. Does the code int pointer myints create a pointer to a pointer of an array of ints, or does it create an array of int pointers? I love this week.
Creates a pointer to an array of ints.
It creates an array of integer pointers.
Oh yes, it does. Ugh.
That's an array of integer pointers. So this is a pointer to a contiguous block of memory that contains, in sequential order, other pointers that point to other integers somewhere else.
And so just for completeness, what would it be for a pointer to an array of ints?
A pointer to an array of ints. A pointer to an array of ints is this. That's a pointer to an array of ints, basically. Why do you point it? Why do you point it, or how do you point it to a type? How do you point to an int type? Oh, how do you point to an integer type? Like this? This is an integer pointer. So this is saying we want to point to an integer. We want to create an integer pointer, and that's what that does. Does that make sense? Or well, what's happening here is, I guess I could just yank out the whiteboard again.
That would probably be a good idea, because I think we've pretty much I think we've covered most of the ground, but just to clarify exactly. Is it just pointers this week, or are we doing anything else?
Just pointers.
Sweet.
Yeah, thank God too, because this is definitely, this is such an important concept, and such a different concept than people are used to thinking about, and it will, your entire successfulness of your C++ career is predicated on understanding pointers. But on the same token, don't be discouraged if they're still seeming nebulous, because this is one of the biggest challenges that you're going to have to face. And once you do, you will be glad. Okay, So then what's that ampersand again? Like the backwards 3, that's the forwards 3. Backwards 3 with a line through it. Okay, so ampersand number. Okay, so let's talk about the stack frame really quickly. Stack frame has 8 bytes of memory, at the very least 8 bytes of memory on it. And so it's going to have 4 bytes for the int and 4 bytes for the int pointer. Both of these variables are going to result in additional memory being allocated when main is invoked. However, let's say that this number contains the value 10. So,
Nelson?
hello?
Yeah, we appear to have done. We've just got hiss for your information, Nelson.
For how long?
Oh, until you said that, for how long? For 10, 15, 20 seconds?
Oh, thank God. I was like, it was 10, 15, 20 minutes. I'd be like, oh, great. Okay, but here's what I'm doing. So we have a size, a type, a value, and an address. Okay. And then, just for completeness, we can do a size, a type, a name, a value, and an address. This table is actually a really good idea. I don't know why I didn't do this to begin with. So we'll have a type, a name. This is number. This is PTR. A size, which is a size in bytes of 4 and 4. Then we'll have an address and a value. Does this table make sense to everybody? And specifically, Wolf, does this table make sense? Because I can explain the table a little bit more. But this is the stack frame of main. So, main's stack frame. So this is main's code. This is main's stack. So this is the memory that is allocated for us when the main function starts. This is the code that resulted in this happening. Yes, segfault, the code is also on the stack, but this isn't the code in memory. This is the literal source that I'm representing here. Okay, so that's a horrible address.
It's missing a D for a start. Still missing a D.
That's still a horrible address. Anyway, okay, so let's say this is at address OX012345. And then 6. Or how about just, I'm trying to think of a better address. It doesn't really matter if this is a valid address. So I'm just going to say this is address 45. This is address 49.
The address is the address is the literally it's the place in the memory of it.
So we'll have memory is addressed by bytes. So we'll have 1, 2, 3, and then so on until we get to 45, which is going to have 4 bytes. It doesn't necessarily, I mean, I don't want to confuse the issue. The fact is the 45th address in memory of my machine that I'm representing here is this. Then we have 46, which is another byte, 47, which is another byte, and 48, which is another byte. And then we'll have 49, which is another byte, and so on and so on. So this number variable gets placed on the address 45. this pointer variable gets placed on the address 49. Okay. So let's talk about the value in each one of these things. What's the value? The value, because both of these are 4-byte variables, the value is going to be the 4 bytes that contain the information. So in the case of number, the value is 10, which means you're going to have 4 bytes representing the value of 10. Oh, and by the way, pretend that I'm prefixing all of these with hex notation. I shouldn't even bothered with hex notation, but I did. Okay. So let's talk about what's in the value. The value of the number variable is 10. Who can guess what the value of PTR is? And again, if I know you know the answer and you know that I know that you know the answer, blah, 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 so on and so on. Okay. The value in this is going to be hexadecimal digit 45. This is the value of the PTR variable. So the PTR variable is a variable. Every variable has a size. Every variable has a type. Every variable has a name. Every variable has an address, and every variable has a value. PTR is a variable whose type is integer pointer, or a pointer to an integer. Now, on a 32-bit operating system, the width of a pointer is going to be 4 bytes. On a 64-bit operating system, the width of an not the width of an integer, the width of a pointer. On a 64-bit operating system, the width of a pointer is going to be 8 bytes. And it doesn't matter what you're pointing to. You can be pointing to anything. The pointer is still going to only be 4 or 8 bytes, depending on your architecture. So what's going on here is that because this pointer has, again, it has a type, and because it has a type, it has a size, and it has to, this variable has to literally take residence in memory. It has to be held somewhere in memory. So it gets a memory address, and that's what the address is. It's where in memory does this variable contain its value. So you'll notice, although this pointer is at address hexadecimal 49, its value is as a pointer to the hexadecimal address 45. So if I do, this is going to suck. Let's see if I can do this right.
Skills with Zs.
Okay, so if I do COUT, shift left, star, PTR, semi, this star operator is going to ask pointer, ask the PTR variable what memory it's referencing. And then it's going to yank that memory and actually have that be the result of the expression. So when I do star PTR, PTR is going to reach all the way into address 45, pull out its data, and send it back into cout. Because PTR currently has the value of OX45.
We've actually reached the point where people are starting to talk about nibbling on each other's bits in BuzzNet. So the thing is, the terminology of this becomes so confusing that you can end up just losing yourself in it.
What would you get if you dereferenced a pointer to a pointer? Well, you get a pointer. See, if I had an integer pointer.
Thank you for just brilliantly proving my point.
And assigned... Are you talking to me?
Where's this taxi driver?
What? Okay. This is a pointer. So let's go ahead and talk about how it'll be laid out in memory. First of all, it'll be 4 bytes. Second of all, it'll be an int pointer. Its name in this case is pptr. Its address is probably going to be somewhere around, at least in this memory addressing system, it'll probably be somewhere around 52, or wait, no, 53. And its value is going to be 0x49. So the value of this variable is the address of this variable. So you'll notice that we have 49 as the address. If we dereference 49, meaning if we dereference this, what we get is whatever this address is storing. And what is this address storing? This address is storing hexadecimal 45. So if we dereference a pointer, the output of this is going to be 0x45. However, if we dereference this pointer, it's going to reach out, ask this address for its value, and this address is going to return a 10. So if we dereference a dereferenced pointer, we'll get the value of whatever the original pointer that you made the pointer from is pointing to. I don't even know if what I said was correct, but you get my point.
Yeah. No, it is. It's very. I mean, it's like following a map to a signpost to a destination. Yeah.
That's very.
Ugh.
Okay. Well, is there anybody else who has questions about this? Because again, we haven't gone over the use of pointers, but pointers are so incredibly useful. And once we start talking about dynamically allocating memory, then things are going to be great. So how are people feeling about this diagram specifically?
Shiny. Yeah, it is probably around about coming up to break time. Or, I mean, what else have you got to cover?
Well, we got to cover dynamic memory allocation.
And
that's it. That's all we're doing. That's all we have time for.
Is that a big chunk of stuff?
No, it's about a 45-minute discussion.
Okay. Can you think of something to set them to do for the break?
No. I can't think. I think they need a break, especially the people
We'll have
who
a break, and then when you have a think, and when we come back, we can get them to do something.
Alrighty. Okay, so pausing the video, and we're back from break. But due to some technical difficulties, this is where the video is going to end. So there should be another video here posted. I mean, after this video, that will be the continuation of today's class. So thanks, everyone. Bye.